Okay, hello, and welcome back again to the other tutorial. And this tutorial is still we are doing data knowledge discovery and data exploration. But we have one goal in mind that we just want to see the impact of the variation with different levels, let's say, of the group, and also of the social economic status, of the gender, and also of the education on the level of, let's say, for example, the brain volume. In order to do that, we just need to install one package. Nonlinear mixed model effect, which comes with the package as it is called NLME, nonlinear mixed effect model. I'm just gonna, I should say, run the command for it, execute that one, and I have it, I should say, installed. And also the first variation which causes differences of the brain atrophy between different, I should say, levels within it, it's going to be the group. Let's explore what is going to be the group and what different components does it have by just executing the line, which is going to be, I should say, for the by running a table and data as a group. You will see that if we just do that, when we execute that, you see that we have three different, I should say, levels within the group. We have, I should say, you see that we have 37 converted. We have 146, I should say, cases that they have been diagnosed as demented, which they have the dementia, and also 190, I should say, observation, which they have, I should say, they have not been identified as being demented and having dementia. And the total of them should add up to 372 observations that we just saw that on the previous tutorial is the number of the rows or the number of the observation. And now, you see that if I just execute the bar plot, you see that the variation and the distribution within each different groups. You see that, for example, if I'm just going to zoom this plot, you see that the number of the non-demented is significantly higher, and that's also what we saw that by executing the line for the table command. But this one is, I should say, a kind of the visualization of the table that we had it before. And also, something which is going to be new for this tutorial is that I'm just going to run this line, which it means that I'm just going to group the data based, I should say, on the group which they belong to. I'm just going to go ahead, I'm just going to call this function, which is going to be called the grouped data, which is a function, I should say, inside the package NLME, nonlinear mixed model effect. And you will see that this function, the group data, comes with, I should say, two-sided formula. Which one, you see that we say that that's the thing that we're going to look for. We are just going to model the normalized whole brain volume with respect to the age. That's the two-sided formula, which it comes as an argument inside the group data. And you see that I have a vertical line, and I'm just going to group that based on the groups which they belong to. You see the groups, they are either going to be converted, either it's going to be demented, or it's going to be non-demented. That's the thing that we either use that by the table command or the bar plot on the previous code. Now, and also the data argument comes with the data that we created here, 372 observation and 15 variables. I'm just going to execute the line. I have an object created here. The data group, you see that essentially it's exactly with the same dimension of the data itself, but this is grouped. And when you plot it, you're just going to feel the usefulness of representing the data when you group that based on the groups that have three levels of the converted, demented, and non-demented. And simply, I'm just going to execute the line as a plot. And you see that the plot is created here, which you see that we have three groups as we did it before. We have converted, demented, non-demented. On the x-axis, I have the age, which you see that it starts from the 60, the minimum of the age, and goes all the way to the 98. And also on the y-axis, for each group, you are going to see the normalized whole brain volume, which I should say it's from 0.65 goes all the way to, for example, the 0.8. We have also 0.88 here, but that's, you see that it's less than 1 because the name implies itself that this is the normalized whole brain volume. Then you see that on the x-axis, this is the age, and the y-axis, that's normalized whole brain volume. You see that for each group, you see that for each group, converted, demented, and non-demented, they follow a different, I should say, pattern. For example, in the converted, with respect to the demented and non-demented, you see that the variation of the brain size is significantly different when you just move from each group to the other one. Although each one, they are decreasing, but they show different pattern of the decrease. You see that, for example, with the non-demented and the demented and the converted, we have different slopes probably for each one, and we see a different variations within group between the converted, demented, and non-demented. And that's the thing that you're just going to take into account when we just want to do the Bayesian hierarchical models in the future tutorials. Okay. And now also, on the next one, I'm just going to move on to the clinical dementia rating, which is going to be for this line. I'm just going to execute the line, CDRS, and you will see that you have, I should say, 4 rating. For 0, which it shows that that person is non-demented, and the score, which is going to be 0.5, which means that it's mild, I should say, cognitive, I should say, impairment, and 1 and 2, which refers to the most severe ones. Specifically, if someone gets the score of the CDR as 2, it means that that person cognitively, based on the cognition, I should say, examination which they show that they have the severe dementia or severe Alzheimer disease then. And now you see that also when we just run the bar plot, you see that, I should say, the visual representation of our observations based on what the CDR scores they have. The most of them, they do not have any symptoms, but you see that 2 of them, they have severe, and some of them, they have mild to very mild, I should say, Alzheimer disease. By saying that, it gives us a good, I should say, reason to just group those data based on the normalized, I should say, nonlinear mixed effect models by using the functions group data. But in that case, again, I have the 2-sided functions, but this time I'm just going to group them based on the CDR, which is essentially the cognitive disorder ratings which they have, and I'm just going to group my data sets. I'm just going to select this line, execute that by pressing Ctrl Enter, and I have exactly the same dimensions of the data sets created, and you're going to see the usefulness of grouping that data by that package if I'm just going to plot the same object which I created. And I'm going to zoom this object, this graph, and you will see that. We had 4 different ratings. We had 0.5 ratings. Sorry, we had 0 ratings. We had 0.5 ratings. We had 1 and we had 2. And for each one, you see that the x-axis represents the age from 60 to 98, and the y-axis represents normalized whole brain volume. For each piece of graph, you see that the same trend, age and the brain volume. But this plot is presented for 4 different groups, which is implied by having 4 different, I should say, groups with respect to the CDR scores. You see that we have different variations of the brain atrophy depending on the level and the score of the CDR which the people get. For example, you see that the slope of the brain atrophy with respect to the patients which they have showed, I should say, severe dementia, which they had the highest score of the CDR, is much steeper compared to the people who have, let's say, for example, either not dementia or they have mild cognitive disorder or mild dementia. And that's the thing which it gives us a clue that when we just want to just get the Bayesian multi-level analysis, we are going to think of the variations of the CDR scores within each individual, which this is localized into different groups of the CDR. Okay, and now we're just going to do the same thing. I'm just going to go ahead, go to the gender. You see this line of code. I'm just going to see that. Okay, what about the gender with respect to the male and females? You see that we have in our group, we have 213 female participants in our study, and we have 160 male participants. But however, if we also visualize that by doing a bar plot, you see that the bar plot is created like that. That's essentially a visual representation of the number of the participants, if they are female, denoted by the F, or if they are male, denoted by the M. We see that the female participants are higher compared to the male, and also it can induces me to look at that fact if group those data sets. I'm going to do the same thing again. I'm just going to use the grouped data function within, I should say, the NLM if, I should say, package, nonlinear, I should say, mixed effect models, and I have two-sided formula, and you see that it's grouped based if they are male or female, the feature which I have, and the data is given also. I'm just going to execute the line. You see the object at the global environment is created with the same dimension as our pure and raw data sets. You're going to see the usefulness of grouping those data when I'm plotting the same object, and you're going to see that. You're going to see that. Okay. The grouped plot, the x-axis again is the age, because that's what model showed to the function. The x-axis is the age, the y-axis is the normalized whole brain volume, and you see that it's plotted with different groups. Female, the lower plot, and the male, the upper plot. Probably it's not going to be very, I should say, tangible and perceptible by the eye to see that if the slope of changing, I should say, the brain volume, that's what we call that the brain atrophy after the age of 60 between women and men is going to be different. Maybe it's going to be so hard by the eye, but that's the thing that we are just going to, I should say, pinpoint it very precisely when we are just going to do the Bayesian models to see that if the rate of the brain atrophy is going to be different between the female and the male participants in our clinical study then. But now we see that there is variations, but how much the variation is going to be different, that's the thing that we're just going to see that when we just run hierarchical Bayesian analysis by writing a piece of code in Stan. And also, we are going to look into the education level. I'm just going to run this code, which is essentially, it's the table of the education level. I'm going to see what is included in this object. You see that here on the console that you have, for example, if those people have, for example, have been in school with only 6 years at the school, we have 3 participants, and we have also 3 participants if they have spent 23 years at the school, and also we have, let's say, in between we have 8 to 20 years of the participants to be at the school. And now I'm just going to also visualize it to see the visualizations of the number of the people who have, the number of the years that the people and the participants in our study they have spent at the school then. For example, you see that the highest one is for the people who have the high school diploma, which means that they have 12 years of study at the school, and I should say they have, I should say the lowest one is going to be for the people with 6 years of school or less than 6, and also 6 years of school, and also people who have obtained high advanced diploma. But the majority, as it seems, it comes with the people who have only the high school diploma, and next it goes, I should say, to the people who have only an undergraduate degree, 16 years at the school, and also a master program, which is going to be 18 years at the school. Okay, now it motivates us to go ahead and use the group data function to group those data sets based onto the level of the educations that they have. We have the two-sided functions, which they are going to be grouped based on the level of the education. You see that the data is created here, data underscore educ, with the same observation as our pure data sets. You are going to enjoy seeing the benefits of grouping those data sets when I'm just plotting that data. It takes a little bit of time, but when you zoom the data sets, you see that we have a multiple of the plots. The plots for each one shows on the x-axis the age, on the y-axis the normalized whole brain volume, and at the same time you will see that we have each, I should say, rectangular. You see that it's the different layers of the school. For example, this one shows those 3 people who have done only 6 years at the school. You see that we have 3 observations and we have 3 dots. And also, for example, for the people who have, let's say, for example, they have been in school for 23 years. You see that there is a slope for that. We have 3 observations, and if you compare that to the people with only 6 years, probably it's not going to be very perceptible and tangible, the difference of the slope. You may also see a minor change of the slope. You see that probably the people who have been at the school for the 6 years, they may have, I should say, a steeper slope in the observation, and I should say when they age, their brain atrophy, it decreases much faster compared to the people who have been at school with 22 years. But if that slope is not going to be that much tangible to you, we are going to see that when we just go to, I should say, our session. Let me close all these email messages which I'm just going to get. And when we just go to, it seems that I'm receiving lots of emails then. Then when we just move on to the Bayesian analysis, you are just going to appreciate very precisely how the slope of the change, how the slope of the brain atrophy changes with the age with respect to the level of the educations of the participants in our clinical studies then. And lastly, we are just going to check the level of the socio-economic status. I'm just going to use the table commands. I'm just going to go ahead with the SES. You see that we have different scores for the social economic status from 1 to 5. The higher number shows that the people that are enjoying the higher level, which means that the majority, they are somewhere in between. And if I do a bar plot, you appreciate visually what's happening there. You see that these ones, the fewer people, they are at the highest level of the social economic status, but the majority, they have been given the score of 2. This one motivates us to group those data again, as what we have done with the NLME package. I'm just going to go ahead with the two-sided functions, group that based on the feature of the SES, and the data is given. I'm just going to execute the line by pressing Ctrl Enter, and you see that we have the same data sets with the same dimension. However, this is grouped based on the social and economic status. You see that the impact of the plot, when you see that we have multiple plots depending on each individual, depending on which group of the SES. The x-axis is the age, the y-axis is the normalized whole brain volume, and you see that there are different patterns and different variations between the people with respect to the brain cell introduction and the brain atrophy with respect to the age. You see that the people with the highest level of the socio-economic status, they may have a different slope with the people, let's say, who are spending their life in, let's say, a lower social economic status. They may have experienced a lower slope and less steeper slope of the brain atrophy as they age and as they grew older. If you do not see that difference of the slope, you're going to see that and appreciate that when we just do that on, I should say, the Bayesian analysis. You're just going to find the slope with a probabilistic distribution as what we're just going to do that